What if humanity could move entire stars? What if civilizations advanced enough could literally steer their solar systems across the galaxy? It may sound like science fiction, but today's guest argues that stellar engines are real engineering concepts grounded in physics. Today on Highway to Space, we explore how humanity might one day pilot the stars themselves. Hello, everyone. I'm Dan Profir, and this is Highway to Space, the podcast where we explore the ideas, technologies, and people shaping humanity's future beyond Earth. Today's guest is Dr. Kelvin Long, an aerospace engineer, astrophysicist, and author whose work focuses on one of the most ambitious frontiers imaginable: interstellar spaceflight and extreme propulsion systems. He is the author of the new book, Stellar Engines: Advanced Spacecraft Propulsion Through Extreme Aerospace Engineering Design, where he explores how advanced civilizations might build colossal engines capable of moving stars, reshaping solar systems, and enabling journeys across interstellar distances. In this conversation, we'll explore the science, the engineering, and the philosophical implications of what it might take for humanity to become a truly interstellar civilization. Dr. Long, welcome to Highway to Space.
Thank you.
Your book explores one of the most extraordinary concepts in astrophysics, stellar engines. What exactly is a stellar engine, and how did this idea first emerge in scientific thinking?
Well, stellar engines, we tend to think of that as meaning an actual engine within a star or some way of moving a star, which is something else I'm also interested in, which you alluded to. But the reason I chose that title was because, of course, fusion reactions is what powers the stars. And I think that if we're really going to travel between the stars, fusion reactions is one of the modes by which we could do that, because fission just won't cut it, and chemistry certainly won't achieve it, although there are other methods. So I see fusion reactions as the kind of agency by which we can literally access the stars by using the same physics method to cross those distances. So it's almost serendipitous that nature has given us the solution to actually reaching those destinations.
Mm. When people hear about moving stars, it sounds almost mythical. At what point does science fiction and real physics begin in this discussion?
Well, when we think about questions like SETI, search for extraterrestrial intelligence, we think in terms of Kardashev civilizations. So those that control their entire energy of the planet or their star or their galaxy. So to do something like move an actual star, you would need to be a galactic-wide civilization. So probably, thousands or even a million years ahead of us. But in principle, it's possible. So although the book is about propulsion, I do actually have some really interesting calculations in there. For example, I allow the reader to attempt to calculate how much it would take in terms of energy if you were to strap lots of rockets to the Earth to change the orbit of the Earth from 365 days per year to 360 days per year, or if they wanted to move the star itself and the entire solar system. Can you calculate that problem? How much energy would it take? Because the sun, of course, is massive. It's 10 to the power of 30 kilograms. And then you've got all the planets in between. So it's a phenomenal undertaking. But of course, the solar system itself is already moving. It's spiraling in and out of the galactic plane around the galaxy over sort of hundreds of millions of years. And the galaxy itself is moving. So actually, everything is a starship in a way. Even the Earth, which is rotating and spinning and is going around the sun. So nothing is really static. And of course, we know this from Einstein's relativity, that there's no real absolute space-time frame.
Mm-hmm. What first fascinated you personally about extreme propulsion and interstellar engineering?
Well, I was first attracted to Project Apollo when I was a young teenager. I saw an exhibit at a museum which really inspired me. I didn't really have a propulsion interest as such. It was more about I wanted to be an astronaut, like lots of children do. But as I got older and I started to get involved with organizations like the British Interplanetary Society, which is one of the oldest space organizations in the world, 1933 they were founded. And they were one of the few organizations actually looking at interstellar flight. So back before the Second World War, they were considering going to the moon, going to Mars, and they were really pushing those ideas. Of course, once we achieved going to the moon, going to Mars was still a goal, but it's what comes next. Once we've explored the entire solar system, what comes next? And it's really getting to the stars. And that's something which I think not enough people are focusing on. There's been lots of physicists like Robert Forward, Freeman Dyson, and others over the years who published papers exploring this subject. And so this really attracted me. I've always been attracted to problems that not many other people are working on. Today, of course, lots of people are working on interstellar flight. I remember in 1994 when the Alcubierre warp drive metric was first proposed in classical and quantum gravity. There was hardly anybody working on that subject. I hosted a conference in London. 65 papers were published at the time on warp drive. Now, of course, there's thousands. It still is a very theoretical Gedanken experiment, if you like. It's not something we can practically build today, but there's people exploring these ideas. So I've got more practical as I've gone on, though, because I started with general relativity and warp drive, and then I moved into kind of fusion physics, and I've also been looking at laser drives. So the thing that I'm interested in is how to get human beings, not just a robotic probe, but human beings to the nearest stars, 4.3 light years away, in something like 100 years. You'd have to go at something like 2,700 AU per year, which is several orders of magnitude faster than the Voyager probes. So there's clearly a lot of technology steps along the way, which space agencies are gradually addressing as part of their roadmaps. But meanwhile, what I'm interested in doing is working on the theoretical problems. Can we design these engines on paper so that they at least look credible? And at some point, when the technology catches up, perhaps we could even build some of these machines. That really excites me.
Absolutely fantastic. I suggest we explore a little bit more the physics of moving star. What are the fundamental physical principles that would allow a civilization to move a star?
Well, as I mentioned, a star is incredibly massive. And so in order to push a star, you would have to have equivalent energy to actually push it over some distance. The book itself doesn't deal with the movement of stars. It deals with transport between the stars. Although, as I said, the idea of a stellar engine, something that can actually move a star, is something I'm also interested in and have written papers on. But this book is mainly about how you transport between the stars, how you take robotic probes or humans between the stars. Of course, some people argue that the journey times to the stars are very, very long. So perhaps you could build world ships. So world ships are almost like large planets or moons. And the book has a chapter on world ships where I discuss something that's 10 to the power of 12 kilograms in mass, which is an enormous vessel, 100 kilometers at length. So these are really almost astrophysical in scale. So if you could build something like that, then in principle, you could push a moon, and then in principle, you could push a planet, and in principle, you could push a star. So these are theoretical ideas which are possible, but it's all about the momentum transport and how much energy it would take to push them, which is enormous. So it's not something we can do in the near future. But who's to say what's possible a million years from now?
Yeah. Well, some proposed stellar engines, as you just mentioned, involve manipulating stellar radiation or stellar winds. I was thinking, can you walk us through one of the most plausible designs?
Well, really, it's about attracting, obviously gravity attracts inversely proportional to the radius squared. And so if you have another mass that's near a star, then you would attract it. And so that's one of the ways in which you could, but that means you've got to get another object. So there were ideas many years ago about there being a sister star to our own star, that there was another star out there. I think it was called the Nemesis theory. A couple of books were published on it. Although I don't think the evidence holds up that it does exist, but it's an exciting idea. And of course, if such a star was to exist and its orbit was to come close to our star, then it would attract our star and kind of pull them together, and they would be in an orbit, and that would of course cause a motion of our star. But as I say, this is not something we can do technologically today, but maybe in in the far future. But the book, although the book is called Stellar Engines, stellar, it really refers to fusion reactions within an engine that you could put in a spacecraft and to propel a vehicle. So it's really taking the physics of what happens in a star, making it very small, something that may be only milligrams or grams in scale, firing lots of laser beams at it, and then causing a fusion ignition within that tiny capsule, which detonates. And then the energy, the charged particles come out of that, the protons, the helium fall. You use that for thrust generation. So that's what a stellar engine basically is in the context of my book. But, you know, as I say, the idea of astrophysically moving something like a star is possible on paper, but it's something that's in the far future. And I think before that happens, we're more likely to travel to the stars ourselves, sending our robotic probes, or you know, sending human beings to those stars. And then it's a question of, well, why would would you want to move a star? I mean, the only reason I can think why you would want to move a star really is if you thought there was going to be a galactic collision and you needed to move your solar system out of the way. But you know, who knows?
Yeah, well, what's interesting about science fiction is that it helps us train our brains to anticipate events. And I would like to say a word about one famous concept involves reflecting a star's radiation asymmetrically to generate thrust. Can you tell us how realistic this idea would be from an engineering perspective?
Yes, I mean, it basically is the same idea as a solar cell. So a solar cell, of course, photons leave the sun, they travel through the solar system, and the idea is to have a reflective surface, which then reflects the photons, and you get 2 times the momentum, and so it pushes the cell. And so it's the same idea. If you could build a structure that was similar in size to a star around it or near to it, and it wasn't to vaporize from, you know, from the heat. Then in principle, you could reflect the photons from the star back, which would then push the star, that would move it. Of course, Newton's equal reaction to every action. So that means the giant cell would also have to move the reflective surface. So you can imagine you've got your star and you've got your cell, and they'll basically be pushed apart. But the consequence is that your star would be forced to move in its position. So if we ever, for example, wanted to change the position of the sun in the solar system, that's one way you could potentially do it. But as I say, it's not something we can do today. But there's nothing in the laws of physics which prevent it. It's really a materials problem because you know, we couldn't actually build a material that could be that close to the sun and take that kind of heat, that radiation. The closest we've sent a probe to the sun is the Parker Solar Probe, of course, which is there at the moment. Mine and my children's names are on that probe, which is wonderful. And that's got really close to the sun, and it's got this huge radiation shield to protect it. Otherwise, it would just be vaporized, all the electronics would be fried. So, you know, how close can we get? But you would need something like that technology, many orders of magnitude in size, wrapped around a part of the sun's surface to asymmetrically direct it, by reflecting the photons back at it.
Yeah, if a stellar engines were built, how fast could an entire solar system actually travel through the galaxy, in your opinion?
Well, in principle, you know, the stars tend to move at 500, 600 kilometers per second. So in principle, if you wanted to move, you'll be going at similar speed. It's more, I would see it more of like a maneuvering system. So you're changing the direction and the orbital position of the sun and the solar system, rather than actually trying to take an entire solar system out of a galaxy. That would be a much harder problem. And I think I would struggle to understand how the system would remain stable gravitationally because of the tidal gravitational interactions between the objects would be just extreme. I mean, everything would just be so disturbed. But you know, we have artificial intelligence, so in the future, could we possibly calculate and predict the position of every single particle, every single planet, every moon, you know, every piece of dust, so that we would have high confidence that the system wouldn't become unstable? I mean, that's what it would require. It would require a supercomputer and artificial intelligence to manage that system, as well as the actual thrust system to move the the entire system, you know.
Yeah, yeah. Well, these projects are obviously far beyond current human capabilities, but what level of technological civilization would be required to build something like this?
Certainly way ahead of us. As I mentioned, we haven't even gone to the stars yet. We've sent the Voyager probes out there, which are at sort of 160 AU, still operating for now 50 years, which is a remarkable achievement. But this is really baby steps. You know, we're only just putting our feet in the water of the ocean of cosmic space. I think we have to think in terms of, you know, certainly thousands of years ahead of where we are today, if not a million years. But it's difficult to predict. I mean, technology is difficult to predict on the long term, where it's going to go. Who I remember growing up in the 1980s, and I would have never thought we would be living in a world full of, you know, the internet and artificial intelligence and how that's influenced the entire world. And of course, we have all the satellites in orbit around the Earth. So who knows where we'll be in 100 years or 1,000 years from now. But it is certainly something that's like a Kardashev 2 civilization, which has complete control over its star, the energy output. So a civilization that could construct a Dyson sphere, for example, would be the sort of civilization that could do things like this. But you know, with automation, robotics, AI, rapid manufacturing, potentially you could build something really quick. Like if you want to build a Dyson sphere around a star, it's all done automated by robots. It's not human beings doing it. We might control the initial part of it, but it's robots who can do it really, really fast. And you think about how with AI at the moment, if you ask it a question, like I uploaded a scientific paper to an AI the other day and asked it to analyze it, and it did it in 1 second. And it probably slowed the analysis down for me. It probably did it in 1,000th of a second. So what could AI do in the future? You know, how rapidly could it build things? If we wanted it to build a space station or you know, habitable moon or something like a Dyson sphere, perhaps it could do it in an incredibly fast timescale. But of course, then it's a question of the materials as well. So they have to strip mine like an asteroid first to get the materials, and then to somehow fabricate that into the right structure that you need to create something like a Dyson sphere or something like a Kardashev thruster around the star that could push it.
Yeah, the Kardashian scale. You mentioned earlier stellar engines also could be used as a survival technology, for example, to move solar system away from a cosmic danger. What other usages would you envisage?
Well, really, I think, you know, stars go supernova, of course. That's an issue for you know, I remember reading the Arthur C. Clarke story many years ago, where he talked about the Star of Bethlehem in the Christian story, and the irony that may have been a star that went supernova that may have wiped out a civilization. Who knows? You know, if there was anyone living around it, the irony of that. So if you had information that suggested your star was going to go supernova, something was happening to the hydrogen burning, the helium burning, and the oxygen and nitrogen, you could see that it was rapidly changing. But we have a good understanding of stars. We don't think that's going to happen to our star anytime soon. But then there may be a sense of urgency, and that your options are really build large ships to move populations off world. But another option is, well, could we actually move the world itself, or at least to a safe distance, right? So, or for example, if our star wasn't even to come supernova, but turned into a red giant, which is what it's going to do towards the latter stages of its life, where its envelope may reach as far as Mars. So anybody on Earth just couldn't exist. But could you move the Earth? You know, you can imagine a civilization of humans in the future who want to maintain and preserve human history, and they don't want the Earth to be destroyed. They want to preserve it, so they may decide, okay, can we move the Earth further out, even though it's going to be colder? So could we use some sort of stellar engine type technology to move the planet? And in principle, you could do that, but I think you'd have to do it slowly because of the you know, the tidal gravitational disruptions that would result from that. And you could potentially rip a planet apart, but in principle, you could do it. I mean, I actually have a problem in the book where I ask, I forget the details, but how many Saturn V engines would you need if you strap them to the Earth to move the Earth, as I say, in its orbit, change its orbital period? And that's a fun calculation. So at the end of each chapter in the book, there are three main problems, calculations based on the chapter, and all the solutions are at the back. And the main idea of the book is to actually teach. So it's kind of like an undergraduate textbook. The way I see it is, if you really want to get into stellar engine, starship engineering, doing calculations on antimatter, interstellar ramjets, that sort of thing, then this helps you to do that. So not only do I give the core material in the chapter, but in the problems I describe problems that you can solve, which if you understand how to do that, then you have a lot of knowledge. It includes things like how to move a world just for fun, you know.
Yes, and I should step in to remind our followers that behind your writing resides a great wealth of research. What are the biggest engineering obstacles that you stand between theory and reality, in your opinion?
For interstellar flight.
Yes.
So actually, I would say that I mean, there are lots of technical engineering problems. For example, I was on the Starshot advisory committee for 7 years, Project Starshot, which was a laser sow-driven initiative to send a small gram scale probe to the stars. And we focused on kind of 20 engineering and physics problems, like don't melt the sow with the laser beam, or how many lasers do we need? Is it ground-based lasers? And how fast do we need to go? And you know, there's lots of engineering challenges, but I think they're all potentially solvable. Like we needed a 100 gigawatt laser, which we can't build today, but we can see that in 20, 30 years, we might be able to. So that's just a question of time and technology maturation. Actually, I think there's no real physics or engineering obstacles to get into the stars at all. They're just technology problems which we can solve given enough effort. And that's where we should be putting our emphasis, instead of, you know, fighting in wars, which is what we tend to do as a sport, as a human race, more than where we should be putting our energies. Imagine if we all focused on, you know, let's take human beings into space and explore other worlds and find life out there. How exciting that would be. What a useful expenditure of our energy. But we don't do that. And I think that gets to your question, which is what's the hardest challenge. And I think actually it's human beings, it's human relationships, it's politics, it's nation states not being able to get on well with each other. This all creates obstacles because as soon as, you know, we made a bit of progress in space. The ISS, of course, is one of the crown achievements, because I think not because of the technology achievements actually, but because of the international collaboration.
Absolutely.
You know, you've had all these astronauts from all over the world: Russia, United Kingdom, Britain, France, America, and they basically all got on together. And even now, which is crazy, where you have the situation going on with the Russia-Ukraine conflict,
Yeah.
but this, you know, Russian astronauts and American astronauts working together on the ISS. And I think that's the gold standard. That's the aspiration to get to, is can we overcome our differences? Of course, you know, China is another country where there are ideological differences, but can we do things in space which have a common benefit for humanity? I think these are the biggest obstacles. This is what it's taught me. I mean, I when I first started getting into interstellar flight, I did think it was mostly engineering and physics challenges, which is what attracted me to it, because I like solving problems. But actually, working with people was incredibly difficult. Human beings are so complicated. I remember Isaac Asimov talking about in his Foundation series. He talks Harry Seldon, the statistician who works on the probability of how to calculate human civilizations. He treats them like particles, like in thermodynamics, that you can predict the future of huge populations of people. And Isaac Asimov actually made the point in an interview that actually, you know, particles are so much more simpler, because there's just a few dimensions you have to consider, like the quantum state, the motion, the mass, that sort of thing, the charge. But human beings, there's so many dimensions to us that we can't possibly calculate, predict, like what human beings, and we can't predict what our spouse is going to do next, or our brother or sister, let alone what a huge population of human beings are going to do. There's a benefit to that. I mean, it means there's so much creativity in humans. We have so much resourcefulness.
A
Um,
surprise.
but it's unfocused, right? So in propulsion physics, we have this concept of collimated engine exhaust. So if you have an engine exhaust that comes out nicely collimated, it means it's highly efficient, so you get really good thrust. But if it's divergent, it's inefficient, right? And that's the way I see human expenditure of energy. Is it's very divergent. It's all over the place and it's not focused. And as a result, we're just chaotic. We're full of creativity, but we're chaotic. So what we need to do is somehow collimate our energies, become more kind of harmonized in how we approach things. And I think we can overcome some amazing challenges. And all those things we talk about, like building engines to get to the stars, or even moving whole worlds, these are all things that are possible in our future, or at least our great children's future, one day.
Great. I love that. If humanity wanted to, seriously pursue interstellar capability, what technologies should we start developing today?
Well, my main research interest is fusion physics, and mainly because I can see it's immediately in our future. I mean, we've been working on a fusion problem. People have said it was 50 years away. It's always 50 years away, but we've now cracked it. Okay, the National Ignition Facility in San Francisco, Lawrence Livermore, has achieved ignition in 2022 with a small target of sort of 2 megajoule lasers, which means that we can do it. It's not just in principle; we can do it. We know how to create a star on Earth. The next question is, well, is it an efficient process? Can we get a lot of energy out of that capsule? That's a lot more energy than we put into it. At the moment, we take that energy from the national grid itself, what's called the wall plug energy, and it's highly inefficient. The efficiency is less than 1%, which is obviously not good enough. But when everything starts big like that, you think about the first computers; they were the size of an entire house, and now we have these smartphones, right? So that's the way I see these kind of fusion reactors. Is that now we're going to focus on the next generation of reactors actually contribute energy to a national grid. And there's other facilities like ITER, the tokamaks in France, which is another project. But it's not just fusion reactions. I mean, there's lots of other ideas. I mentioned Starshot, which is laser cell technology. We know how to build lasers. We know how to build cells. Put several solar cells in space. The Japanese Space Agency put Icarus in space. The Planetary Society in America put a cell in space. So we have put cells in space, and we've demonstrated the technology. I think we need to be pushing that a lot more. Once you go out past Mars, I think the utility of solar cells really drops because the solar pressure drops significantly, especially out in the gas giants. It's really, really low, so you don't get a lot of benefit from it. But within the inner solar system, kind of Mercury, Earth, out to Mars, I can see a lot of benefit with solar cell technology. For interstellar flight, it's still possible, but you really have to get close to the sun, and you need a large surface area in order to get sufficient thrust to push an object. But there are so many ideas out there. There's nuclear Orion type technology, which is sort of detonating huge explosions behind a vehicle. Something we've been able to do since the 60s. That was a backup plan for Saturn V. Not something I would necessarily advocate we should be doing, but it's just another approach we can do if we thought there was an asteroid that was headed towards us and we needed to mitigate that existential threat. There's antimatter, of course. Antimatter is really the golden thing we would aim for. 90 billion megajoules per kilogram, way more than fusion even. But the problem with antimatter is we don't know how to make large quantities of it. CERN makes something like 9 antimatter particles a year. We don't know how to actually contain it, because once you contain it with any matter, it self-annihilates. So there are ideas that I'm exploring for antimatter catalyzed fusion, which is where you're dealing with fusion reactions, but you inject in small quantities of antimatter particles into the reaction, which can massively amplify the amount of energy you get out. So there's so many ideas. And of course, then we get into, you mentioned science fiction, and we get into some of the more fantastic concepts like the warp drives and the wormholes, which are actually based on solid grounds of general relativity. Albert Einstein, 1915 paper on general relativity. So, but the problem is they require enormous amounts of negative energy, which is not something we know how to create at scale. We have something called the Casimir effect, which is when you take 2 plates and you push them very close together, you get this negative energy which is created, and it's been measured in a laboratory. For decades, we've known about this. So we know that negative energy can be created in principle, but at scale is a major challenge. I have a colleague, Dr. Sunny White in America, who's actually trying to build devices that deal with generation of Casimir energy to power things like silicon chips and stuff, and I think if that kind of technology can be proven to work, that has enormous potential. And he has an eye on warp drive type technology. And the reason you need negative energy is because in order to manipulate gravitational objects like stars and planets and stuff, you really need something that's anti to the gravitational pull, which is what basically negative gravity is, negative energy is. It's something that has negative pressure. So that's how you could manipulate gravitational fields. But these are concepts which we don't know how to do today, but they're on paper. And I mean, I would love to see more students getting involved in calculating these sorts of problems because they're very exciting. They teach you a lot of interesting mathematics and physics, and some of them might actually come through.
Yeah, yeah. And that leads me basically to my next question to you. Most propulsion concepts today aim to move spacecraft, but stellar engines move entire planetary systems. And the question is, why might that approach make sense?
Well, as I mentioned, the only reason you would really want to move an entire planetary system is if you thought there was such an existential threat that you didn't have, maybe the population is so great you just can't move everybody off world. I mean, if there's like 8-9 billion people on the Earth today, I forget the exact number, but if it was 50 billion people, you can't possibly move 50 billion people off world. So that's then the question: well, can we move the world
Together?
If we were given sufficient time, we knew something was going to happen. We certainly we are smart enough to know how to engineer something so that in, say, 100, 200 years, maybe, we might be able to put in place a technology which altered the orbit of the Earth slightly, which might, have an effect on our climate, which could be desirable, for example. But, to actually move a world, it just, because the problem is it's so massive. The Earth is 10 to 24 kilograms in mass. It's a million times less massive than the sun, but it's still very big. So, perhaps if we start off smaller, we've been able to push vehicles first. So, we can push things like the Voyagers and so forth, but can we push a vehicle with human beings on board? Imagine the International Space Station with an engine behind it, 450 tons being pushed. And that's a problem in my book, by the way, to work out. Could we push that? Then can we go bigger? Something like a small moon. One of the problems I deal with in my book is taking an asteroid and actually hollowing it out and then pumping in an atmosphere and building a city inside of it. It's called an asteroid starship. Again, this is an idea that goes back to science fiction. And then you put some engines on the back and you essentially, instead of building a huge spaceship, you just use an asteroid and you make it habitable inside. And that sounds like a credible way to go, as long as you can control its trajectory. I mean, you wouldn't want to be living on an asteroid in an asteroid belt, for example, because there might be collisions and, who knows. But that's one way to go. And they're already traveling quite fast. I mean, we've had recently all these comets coming into the solar system. You have 3I Atlas and Umar and the others, Borisov. And they're all traveling quite fast. I mean, 3I Atlas was the fastest, sort of 60 kilometers per second, I think, at one point. And the others were sort of 30 kilometers per second, which is what you expect when they're coming from interstellar space. But that's sort of much faster than we can do today. The Voyagers are traveling sort of 17 kilometers per second. So if we could just get onto one of those comets, even, perhaps that's a way you could transport around the solar system and then outwards to whatever lays beyond, at least out to the Oort cloud. Could we hitch a lift, land a spacecraft on a comet, for example, and just allow ourselves to be transported out? And before you know it, I mean, imagine if we had landed something on 3I Atlas, we'd be out of Jupiter by now. And then, in a year's time, we'll be out there in the interstellar medium. So that's other ways we can approach the problem. But at moving anything that's massive requires enormous amounts of energy. And, I mostly deal with reaction engines, which means thrust. But there are other ways to do it, as we've alluded to, like solar cells.
Listening to you, a question springs to my mind. Could we ever detect evidence of alien civilizations using this stellar engines somewhere in our galaxy?
Absolutely, yeah. And this is an active field of research. In fact, as far back as the 1990s, I think there were papers exploring the idea of gravitational lensing, micro lensing of kind of wormholes. So if someone was to construct a wormhole in the universe, it would have gravitational effects, which causes this what's called micro lensing. So you get kind of like a rainbow effect around the lens, and you could detect that through your telescopes. You could see it. So people have actually searched for those. If someone was to build a Dyson sphere, In principle, I mean, there's the Tabby star. People were looking at that and saying, well, is that a Dyson sphere or some structure? But yes, in principle, most of the information that comes to us from the cosmos is electromagnetic. So it's radio waves, X-rays, gamma rays, optical, visible light spectrum. And so if we just take the visible light spectrum, if you're looking at a star and you see some dimming in that star, well, is it because it's a variable star, is a pulsar, or is it because there's a motion of a planet, which now we've detected thousands of these exoplanets, and that's one of the ways you do it, from looking at the dimming of the star. But could it be there's something else? Could you be detecting a drop in the light of a star, and as more you examine it, you might discover that the actual structure that would be necessary to give rise to that light pattern, that light spectrum, is kind of unorthodox and not just a planet in an orbit around the object. And that might indicate some kind of technological structure. So we can, in principle, search for these things. One of the ideas I'm very keen on is what's called a focal mission. So the idea of sending a telescope out to sort of 1,000 AU, because what happens then is you have this gravitational lensing effect on the sun, where images are amplified by something like 10 to the power 4 to massive amplification. So at the moment, if we put a telescope in orbit of the Earth, like the Hubble Space Telescope, and we look at Proxima Centauri, we can see a certain amount of information, but the resolution is limited. But if we take a telescope out to 1,000 AU in the opposite direction and then look back, because the light that travels from Proxima is bent around the star, around our star, it's amplified, and you could get so much more resolution. So these are some of the things we should be looking at doing. And I think that will then enter a new domain of searching for technological signatures, because our resolution is so much improved. Of course, you can't beat sending a spacecraft to another star or to another exoplanet and having actual in situ reconnaissance. The resolution is unparalleled. And if you can actually put a Voyager type spacecraft in orbit around one of the exoplanets of Proxima Centauri, you fill up with instrumentation and you just radio back what you see. I mean, the information is amazing that we would see, and we may detect enormous signs of life. We may detect basic chemical reactions, or even civilizations that we can't detect currently.
Priceless. Yes. Your book sits at the intersection of astrophysics and long-term civilization planning. How should humanity start thinking about deep time engineering projects?
Well, I think it's really about technological roadmap, which is, if you look at all of the space agencies, they do have roadmaps. They think about where we're going to be in 2025, 2030, 2035. But I would say that they lack vision. I mean, they have a mission statement and a vision statement, but they're always really focused on the moon, Mars, which is logical because that's our next steps. It's where we should be going. But I think we need to be thinking much further afield. Even Elon Musk, when he talks about multiplanetary species, he's really focused on Mars historically. He's now talking about the moon more, but Mars has always been his interest. But I think we need to go much further than Mars. I do see Mars, however, as a test. Like, if we can't crack Mars, if we can't demonstrate that human beings can live on Mars, then it's going to be very difficult for us to get out past that. So Mars is to me, is like the test of human character, whether we can survive in space in different planetary environments. But if we set a technological roadmap for what needs to be achieved, like if you want to build a starship that was powered by a fusion engine and you want to launch it in 100 years from now, then obviously you need to put in place technology steps in between. What do we need to achieve in the next 10 years, in 20 years, 30 years, in a laboratory, in numerical codes, in space demonstrators? What do we need to put in orbit? And you kind of build up in scale to that mission. So you build up in energy, in power, in size, in mass, and so forth, and thrust, and eventually get there. That's why I'm interested in projects like the Vasimir, which is a spacecraft design of the astronaut Chang Diaz, because it uses radio frequency heating, storage of fusion fuels, potentially like hydrogen and helium, and it has technologies in it like magnetic nozzles and so forth, which you would need for a fusion engine. So although it's not a fusion engine, and it's something that potentially you could use for in-orbit activity or even going to Mars, it's on the roadmap to get in there. So if you can do technologies like that, it teaches you all of the things you need to do to build a starship based on fusion reactions. which is very hard to do. And there's no doubt about it. I mean, although I think about starships all the time and I do a lot of calculations, there's no shying away from the actual difficulties of the challenge. They're all overcomable. I wouldn't say it's impossible at all. It's entirely possible. But there's no doubt that, because you're going up in scale and power, in energy and cost, everything becomes difficult by orders of magnitude. But what really begins to change things is once we've lowered the cost of getting to Earth orbit, at the moment it's sort of like $25,000 per kilogram, but if we get it down to something like $1,000 per kilogram, then this opens up space, which means, organizations like Asgardia, which has ambitions for building human civilizations in space, will be able to do that, right? You'll be able to build own colonies in orbit because it's cheap to get into space. And then once you can do things in space, you can access the asteroids, you can access all the materials, the minerals, and then building a starship just becomes a much cheaper exercise. Because you're not doing it based on, at the moment, when I try to calculate the cost for these vehicles, and I do, and they tend to come into the trillions, as you can imagine, it's based on scaling of Earth economy. But in the future, that's not where it's going to be. For example, if you were to build a fusion engine, you probably want to go with helium-3, which you can get from the moon or you can get from the gas giants, Jupiter, Saturn. But then you've got to mine it. Helium-3 is great because it's got helium-4 and protons, which are both charged, so you can direct them for thrust. And it produces enormous amounts of energy, but 340 million megajoules per kilogram. But the problem is you've got to mine it. So you've got to actually go into the gravitational well of Jupiter or Saturn or wherever you're getting it from, Uranus, and you've got to extract the helium, and then you've got to separate the helium-4 and the helium-3, and then you've got to put it back into orbit somehow. All of this requires energy and it requires infrastructure. And that's why people tend to think, well, when can we build the first starships? Maybe it's several hundred years in the future, because you've got to put in place the infrastructure first to actually support it. But I tend to think that may be the case for human probes, but actually I think we could do a robotic probe this century, and that's something I advocate for, is to launch in such a mission before the year 2100. And projects like Starshot, which is a laser cell initiative, go some way towards achieving that. I mean, they actually set out with the aim, $1 million project, to actually, can we design a vehicle that we could push using 100 gigawatt laser to the stars? And in principle, we can, but there are some physics and engineering challenges. Building lasers big enough to give that kind of power is one of them. But we can see that it might be possible in 20, 30 years from now, we could do that.
Yes, that's amazing. You touched base earlier with imagining humanity 100 years from now. I would push you a little bit more and say, when you imagine humanity 1,000 or 10,000 years from now, what role might stellar engineering play in our human destiny?
Well, that's a really complicated question, actually, because I mentioned AI earlier, and we're living in unprecedented times. I mean, I remember when I was young, there was no internet. When I was growing up in the 80s, there was no internet, and now it's just the entire world is connected. And now we have AI. 5 years ago, there were people that talked about artificial intelligence, like Werner Vinge, mathematician, science fiction author, and others. But it didn't really exist, and now it's everywhere. Everyone's using it, and we have other technologies going on, such as, for example, the ability to grow organs for human beings, like whether it's lungs or hearts. In principle, we know how to regrow every organ in the human body, and at some point, we're going to crack the brain. At the moment, we don't have enough knowledge about the brain, but you can imagine, when people talk about in transhumanism, people talk about extension of human lifetime. That some people will choose, if you can actually capture the entire consciousness that's in the brain, could you put it into a new body? Okay, and then it gets a more complicated question, because then we've also got the integration of human beings with AI. So it's at the moment it's two parallel tracks. Humans are evolving, we've been evolving, and you've got AI, which is now evolving really fast, and they're starting to converge. And this is where you have projects like Elon Musk's Neuralink, which aims to sort of increase the processing power by a factor of 10 of human thought capacity. So you can see this integration occurring. And I think one of the first things that's going to happen is you're going to have a kind of cladogenesis of human beings. In other words, some people will embrace this future. They will say, okay, we're going to emerge with this technology, and that's okay because I can see the benefits. Like a lot of the diseases that ail our civilizations, like Parkinson's disease and ALS, which destroyed Stephen Hawking, they will be solved. But you're giving something up because you're giving up parts of your humanity. What does it mean to be human? And so I think some humans will reject that, and they will say, well, no, the purpose of humans is to live a life and to experience all the joys and the lows of life. They don't want to be embracing that technology. But for those that do move forward and evolve with technology, then it becomes even more interesting question. And Arthur C. Clarke used to talk about this. Arthur C. Clarke used to talk about the purpose of life as being the processing of information. I don't entirely agree with him. I think that's a part of it. But and I met Arthur C. Clarke, and he was an amazing writer, one of my favorite writers. But one of the things he said in his early books, going back to even like the 60s, I think, and 70s, was he was talking about we won't just be able to fly the starships and drive the submarines and the ships. We will become them. So the question is, at the moment, when I think about sending human beings to the stars, I see it as like, human beings in a vessel, and we are the passengers and the crew, and there's a machine around us. But in 1,000 years from now, it may be that distinction is so blurred that the starship effectively is us, right? Because we've merged with it. And it may be that human beings are just fully integrated into the technology of that starship. Or it may be that we don't send biological beings, we send essentially robots or synthetic life forms, but there's no much difference between them and us, because they have all of the capacity of human beings. Once we've understood the human brain, they essentially are us. They're our representatives. And when I tend to think about the possibility of extraterrestrial life coming here, I think that's certainly how they would do it. Rather than sending biological beings, I think that they would probably send synthetic organisms, because you think about fast accelerations as well. There's a limit to what we can take, and think about jet pilots and how many Gs they can take. Well, if you can accelerate a spacecraft very, very fast, and you're not worried about the biological implications, then that's another way you could do it, is with synthetic life forms. And so, of course, another way is to actually send embryos, and then once you get to the destination, then grow them at the destination, which is another way to do it.
That leads me to a final question. If humanity ever builds its first stellar engine, what do you think that moment will represent in the story of our species?
I think it will be a significant achievement. It will be a significant achievement in history, as significant as some of the other things in our history, like when we built the first computer, or when we built, when we figured out the atom and quantum theory, and when we figured out that the universe was expanding and accelerating. All these are paradigm shifting ideas, and I think the idea of actually building a ship that can go to the stars, it's been a part of our science fiction and our visions for such a long time. The point that we do it, I think it will become routine, just like going into space today. You think about to 1957, the first when Sputnik went up, and everyone was like, "Wow, there's a satellite going around the Earth." And when we first landed on the moon, and well, space has become pretty routine. And I know Neil deGrasse Tyson talks about that, the routineness of space. And I think that eventually, in the moment it's happening, it will be significant, and the history books will talk about it. But I think it becomes so routine that we will just think it's just another thing we do. Just like, today we have the internet and we just take it for granted. And that's what human beings do. And then when we get on to the next thing, which is maybe what it is, okay, can we get to another galaxy rather than just another star? Maybe that's the next thing. Or can we leave the universe, travel to another universe? So there's always, that's what I like about this reality, is it's always something in front of us which we can all strive for, and that makes life interesting.
Dr. Long, this has been a fascinating journey from the physics of stars to the future of civilization capable of reshaping the cosmic environment. Your book, Stellar Engines, Advanced Spacecraft Propulsion Through Extreme Aerospace Engineering Design, challenges us to think far beyond rockets and satellites, and to imagine a future where humanity might one day engineer on the scale of the stars themselves. Thank you so much for your joining us today on Highway to Space.
Thank you.
And to our viewers, if you enjoyed this exploration of extreme space engineering, make sure you like, subscribe, and share this episode, because the road to the stars begins right here on Highway to Space. Per Audacia ad Astra.
Hey, space dreamers, this is Dan Profir, broadcasting live from